we got quite caught up in the concept before, so I just really want to, even though I know, and I say a lot, mathematics is not about the processes and algorithms, at the same time, I want you to master the processes and the algorithms, because then you can focus mentally, like you can have some critical thought and worry about what's worth worrying about. So here's the question, it's a very simple setup. You got square root of x, y equals x cubed. They want the area between those, and maybe you want to start drawing your diagram now because the diagram and its construction is one of the key skills I want you to develop right now. The area between those is this here. And as you can see by my arrow, which I've already put on there, we are going to be rotating around the x-axis. Okay, so having got the area I want, and this is the rough outline of the shape I'm going to get when I do my revolution, I want to do this by cylindrical shells. Clearly, I could do this by annular slices as well, but I'm trying to rehearse this new skill. So, here's what's going to happen. What's the key difference between cylindrical shells and volumes by slicing? What's the key difference? It's a difference of direction. What is it? Okay, yeah, so I'm not going to use the word slices because I'm not going to get slices right now, but the strips, the area that I'm going to rotate is...
They're parallel.
They're parallel to the axis of rotation rather than perpendicular to the axis of rotation. Okay? Get used to saying that. Have that language. You don't want to be in that point where you're like, wait, what am I doing again? If you can't articulate it, of course you're going to have trouble doing it. Okay? So here's what I've got at the moment. I'm sort of struggling for colors here. I used a lot more colors when I was drawing this, but here I've got 4. So I want to put in one of these strips, right? Something like, say, this. Okay, so there is one of my strips parallel to the axis of rotation, and I'm going to rotate it around and hopefully get a cylindrical shell. So it looks something like, let's see here, it looks like it's going to be roughly equivalent to here. There's the opposite side, right? And you must absolutely draw a cylindrical shell that corresponds to something on your diagram. Okay, how does it look? Are you convinced? Yes, it's a pretty busy diagram, which is why it's got to be big. Okay, I've said before, I've talked about the palm rule for these. I kind of think for any volume by slices or cylindrical shells, I'd go hand, man. Seriously, look at how busy my diagram is, and my one's huge. Okay, so there's my diagram. Now, I need some pieces of information on this. For the volume of a cylindrical shell, the easy part is to work out the thickness of it. That's going to be something like this. Which axis is my thickness going along?
Y.
It's the y-axis, right? Because it's parallel here. So this is going to be our delta y. Okay. What else have I got here? I'm going to need a radius. What orientation is the radius?
Y.
It's also y. So in fact, this distance here, the radius of my cylinder, r, is just equal to whatever y coordinate I am at. So that's nice. The last part is the trickiest because of the orientation I've got. It's the height, here. Now what I've tried to do by putting my graphs, y equals the square root of x and y equals x cubed in different colors, is to try and highlight to you, okay, which one is which. To get this height here, clearly it's a difference, right? It's a subtraction of one from the other, okay? What do I subtract away from what? Which one's which? Remembering that I am on a horizontal axis here, right? This black curve I've just highlighted, this x value is going to be bigger, whereas this blue one over here, this x value is going to be smaller. Do you agree? So in other words, I want the horizontal black value, take away the horizontal blue value. Yes, you see where I'm at? The problem, the tiny problem I have, is that I don't have the x coordinate as it's not the subject of these equations. So I need to make it the subject, right? I need to know for the black one, what's x equal to, and then for the blue one, what's x equal to. Thankfully, not that hard. What is it for the black one? The cube root of x, yeah. Sorry, cube root of y, beg your pardon. And then for the blue one, the smaller one, it's just going to be?
Y squared.
Yeah, cool. That's not too hard, okay? So I've got my diagram. I'm pretty much ready to go now, okay? So the way I actually state it in my working is I say, for this cylindrical shell, Because as you know, if you're doing it by slices, hopefully your diagram is good enough that you can see, but there's a radius and a height on a slice as well. So if I say this right at the back, it's very clear what method I'm taking. For this cylindrical shell, the radius is just equal to the height of my coordinate, and the height of each shell is going to be black, take away blue. Nice and easy. That's the cube root of y, take away y squared. Are you happy with that? So now I'm ready to say, okay, what the volume is, and therefore add a whole bunch up. So therefore, the volume is equal to the limit of, okay, what's changing? Delta y is approaching 0. Okay? Therefore, since everything is in terms of y's, right, because that's the axis I'm looking at, I'm going to need y values here, right? So I actually need to know from here all the way up, where do I end? Okay? Now, these are very easy graphs. Maybe you can tell. Where do you think the x cubes and root x curves meet? It's going to be 1, 1, isn't it? So, in fact, I'm going from y equals 0, that's the smallest one, up to 1. Okay? And then what happens in here? Well, this is going to be 2 pi RH, right? Which in this case is y times the cube root of y minus y squared. Yep. So that's my 2 pi RH. I'm missing one piece. The thickness of my cylindrical shell. Cool. And that was all the hard parts. The visualization, the working out which bits which and how they interact. And from here, it's actually very, very straightforward. I'm now going to turn this, I'm going to turn this into an integral now, rather than my sigma notation. And while I'm at it, I'll do some simplifying. So my 2 pi, that's constant, comes out. This goes 0 to 1. I'm still going to leave this as a product, but instead of writing the cube root of y, I want to make it easier for my integration. So in fact, that's y to the power of a third, okay, minus y squared. And that's a dy now rather than a delta because I've integrated. And in here are just index laws, yeah? Just index laws. So that's y to the 4/3 and, cool, integral. Well, hold on. Power goes up first
7 on 3.
to become 7 on 3, and then I've got to divide by that power. So there's a 3 on 7 at the front. Yep. Take away y to the 4 on 4, or a quarter y to the 4 since similar format. From 0 to 1. This is nice. 2 pi times.
3 on 7 minus 1 on 4.
Yep. And I've already crunched this. I'm pretty sure you're going to get 5 on 28 in here, and there's a 2 there, yeah? So 5 pi on 14, and I'm working out a volume. So I'm done, okay? So you can see, it's really nice. If you know how to do cylindrical shells, the algebra comes out simpler because there's squaring that you get to avoid. That's really great, okay? And once you master it, it's like, oh, okay, this is not so bad. It looks a bit intimidating when you see this and when you see that. But it's like, oh, this is not that different because you're getting more familiar with what's under the hood. Okay?